Okay. So it is a pleasure to have today with us in our Bar Ilan University Vision Science online seminar, Professor Alon Hafri from the University of Delaware. Alon did his BA in music at Wesleyan University and has an MA and PhD in psychology from the University of Pennsylvania. His PhD, which was supervised by John Truswell and Russell Epstein, was focused on event structure in vision and language. He then did a postdoc at Johns Hopkins with professors Chaz Firestone, Mick Bonner, and Barbara Landau. After that, he joined the Department of Linguistics and Cognitive Science and the Department of Psychological and Brain Sciences in the University of Delaware, where he's the head of the Perception and Language Lab. In his research, Alon explores connections between language and vision in the mind using behavioral and neuroimaging techniques. He's also interested in language and thought, psycholinguistics, visual perception, cognitive neuroscience, and he investigates these from exciting, new, and fresh perspectives. So we're very excited, Alon, to have you with us to hear about your research. Thank you so much for joining us.
Great. Yeah, thanks for being here, everybody. And thanks, Sharon, for the invitation. So it's really a privilege to speak here at the Bar Ilan Vision Science Seminar, which even just this year featured a list of stellar researchers who use a range of techniques to investigate visual perception at all levels. So it seemed fitting to start my talk off with a big picture question about perception. And that is, what is it in the first place? So an influential tradition in vision science provides us with a definition. So David Marr famously described visual perception as the capacity to know what is where by looking. In other words, vision is the process of discovering from images what is present in the world and where it is. And it's fair to say that this conception has set the agenda for decades of perception research that has followed. For example, if you've taken or taught a perception class, you've probably seen images like this, or like this, or like this. And what's happening in these examples is you have an object here, this hang glider, it's got certain colors, it's moving in a certain direction, and your visual system segments the object from the background and extracts and binds features to that object. So your visual system represents what objects and features are present and where they are. Well, is that all? So just take a look at this image. What do you see? Well, certainly some what stuff and some where stuff. So the colors, the shapes, the locations of these two objects. But beyond the objects themselves, you may appreciate something else, that they can fit into one another. And this impression captures a relation. And that's a property that holds between the two objects beyond any property each single object has on its own. And so relations touch almost all corners of cognitive science, including linguistics, cognitive development, analogical reasoning, but they're much less emphasized in visual perception research itself. Vision science textbooks devote chapters to motion, to color, space, and even objects, yet there are no chapters devoted to relational properties like these pieces fitting. And even at the leading conference for our field, Vision Science Society meeting, or VSS, there are sessions devoted to things that get near to this topic, but it's rare, if ever, that a session is devoted to relations per se. And some properties of relations may make this understandable. So for one thing, the puzzle pieces themselves stimulate the retina, but no part of the retinal image exactly corresponds to the fitting relation in a way separate from the objects themselves. So you might think that relations like this don't really belong in vision science, but are really just for the domain of higher level cognition. But in a month from now, many of us will be at VSS on the beach. And of course, rich scenes like this are teeming with all sorts of relations. Physical ones like these drinks resting on a table, and social ones like these people chatting with one another. And relations like these have some really interesting characteristics that make them exciting to study from a vision science perspective. But there are also properties we might not be so used to thinking about in our field. So consider this simple image, a cat on a mat. And notice that it differs from a very similar image involving a mat on a cat. These two images have the same objects and even the same relation, and they have many visual properties in common, but what's different is the roles that each object plays in the relation. In other areas of cognitive science, this is sometimes called the structure of the relation. And they're also abstract, so they generalize beyond particular objects and low-level visual differences. So for example, take this book on a table, a cat on mat, or cookies on a plate. Even though they're very different objects, they're all instances of being on. So can we find evidence that relational structure and abstraction emerge in the course of visual processing? And how can we get traction on this question? Well, rather than asking people what they see, to describe or rate whether something looks like a causal or social interaction, our general approach is to have people perform easy visual tasks that they can do really fast, and that has nothing to do with relations. If we find evidence of relations creeping into these very fast orthogonal judgments, that's evidence that these relations are extracted rapidly and automatically. So in today's talk, I'll present two sets of case studies that exemplify this approach to reveal how structured abstract relations arise from visual processing. And in the third study, I'll explore how relational representations are composed or built up from their parts in time. So just a note on the structure of the talk, I'm happy to take some straightforward clarification questions during the talk. Just raise your hand or interrupt, but let's save the more big picture questions for the end. Also, my video keeps getting blurry, so just ignore that part. All right, so let's get to the first part of the talk. First, I'm going to describe a set of studies that show how visual processing extracts relational structure. And this is work done with John Truswell and Brent Strickland. To ask about relational structure, we'll examine a specific kind of relation, and that is events, or who did what to whom. So if you take a look at this image, you'll notice that you can see the colors, the textures, and even the objects automatically and without effort. And we can even appreciate that some pushing is happening. But beyond this, we can also appreciate who pushed whom, that there's a boy pushing a girl and not a girl pushing a boy. And this is what I mean by extracting relational structure, identifying which person is performing which role. So inspired by the study of semantic roles in linguistics, I'm going to use the term agent to describe the one acting on the other person, and patient to describe the one who's being acted upon. And these roles are abstract. They generalize across various events like pushing or throwing. So what's the role of visual processing in extracting this kind of structure? Well, one possibility is that this structure emerges only from deliberate and intentional reflection about more primitive visual elements. So there's a boy here, there's a girl there, there's some pushy stuff happening. The boy must be pushing the girl. Or perhaps there's some sense in which this structure also emerges rapidly and automatically, simply from attending to the individuals in the image. And so we're going to empirically test that possibility here. So the logic of this study goes like this. We'll show a continuous sequence of images depicting different actions. And on each image, people just perform a really simple task. So that's, where's the blue person? He's on the left here, so people would just press the left button. So even though the task has nothing to do with the event, can we find an influence on a relational structure on these simple judgments? If so, it means that people were automatically encoding this relational structure. So to lay out the predictions really concretely, imagine on one trial, the target, the blue guy, is the agent. Now, on the next trial, he might still be the agent, so his role repeats, the event structure is the same. However, he might switch to being a patient. So here, his role has switched and the event structure has changed. We expect people to respond faster when the role repeats than when it switches. And I'm going to call these role switch costs, but you can also think of them as role repetition benefits. So we used 10 different events, and they were fully counterbalanced. The blue guy was on the left and right. He used the agent and patient in all images, so we had 40 images total. But here are the 10 events. Now we can actually try a demo. So you're going to do this task. Your task is to search for the blue person as fast as possible. So you're going to tap on your desk with your left hand if he's on the left, and right hand if he's on the right. All right, let's try it. Okay, left, right, left, left. Okay, so you guys probably experienced it. This is really easy. It's trivial. And in our experiment, people performed really fast. They responded with under 400 milliseconds and almost at ceiling in accuracy. So since we're close to this performance ceiling, any effects we find will be pretty small, but they'll be really telling. And so specifically, we're going to ask, will people be slower when event roles switch across trials? So here are the results. On the y-axis is the difference in response times when roles switch minus trials where role repeats. So positive values here indicate a role switch cost, a cost when the structure changes. And we find that, yes, people were slower when the role switched from one trial to the next. Now, although this is numerically small, it was super robust and reliable. Almost every subject and category of event showed this effect in our study. And it has the hallmarks of being a rapid and abstract process. So, for instance, it's rapid, so people responded within 350 milliseconds, and this can be thought of as sort of an upper bound on the timing of the extraction. And the effect showed spatial invariance. So the effect was the same even when the blue guy switched from one side to the other. And finally, it was abstract. It generalized across categories of events, like tickling to slapping. So I think these results are really exciting because it provides evidence that relational structure is extracted rapidly and automatically from visual scenes. Now, of course, we want to rule out some alternatives. So for example, that the effect is not just due to some really big changes in posture. So you can see here that agents tend to have more active body postures with their arms and legs outstretched. So in the next experiment, we'll directly test this alternative possibility. So we ran the same paradigm as before, but there was one change. We edited images so the actors always faced opposite directions. Now with this manipulation, their postures are preserved, but the interaction between the individuals was eliminated. So if the previous effect was completely attributable to just changes in posture of the target individual, we should see the same effect as before, of the same magnitude. But if it's due at least in part to the relation, this manipulation should reduce or eliminate that switch cost that I showed you before. So here are the original images. And here are my beautifully photoshopped versions of those images where the individuals are facing away from each other. So I'm going to show you the previous results again, which is this one. And here are the results for the new experiment. So we found that the role switch cost was reduced when their postures were preserved, but the interaction between individuals was eliminated. And I just want to point out, this is not just a result of a ceiling effect, because in this new experiment, people actually took longer to respond. So I think this result is strong evidence that the effects we're seeing is not just about changes in posture, but the best explanation is that we're really finding rapid and automatic extraction of event structure itself. So in a final experiment for this section, we asked whether this effect replicated across stimuli and task. So we ran the same paradigm as before, but we had photographs featuring men and women, and people just had to identify the side of the male individual. So here are some example images, and you'll notice here that even the specific individuals and the settings differ. Yet despite all these drastic visual differences, the effect replicated. So returning to the outline, so far today I've shown that relational structure is extracted rapidly and automatically from visual scenes. So structure is one core characteristic of relations. And next, I'll share a set of studies in which I show that abstracting relations away from their objects can produce some surprising errors. And this work was done in collaboration with Mick Bonner, Barbara Landau, and Chaz Firestone. So to start off, take a look at these images. When these objects are combined in a certain way, they instantiate a relation, containment. And notice that we can appreciate other examples of containment, like this one, even some novel or unusual ones, like this, or even a baby in a box. So these images here all have a commonality. And it's one that distinguishes them from the images on the right. And that's their category of relation, in on the left, on the right. Appreciating these commonalities is a form of abstraction, so representing the relation apart from the participating objects. What's the role of visual processing in this abstraction? Well, we empirically investigate this question by looking for a hallmark of abstraction, and that's generalization from one instance to another. So for example, when we see fruit in a bowl, maybe we automatically process it in such a way that it appears visually similar to other examples of in and distinct from examples of on. So here we ask whether relational similarity is so powerful that it can produce confusions between images, even when those images have completely different objects and visual features. So to explore this question, we collected common household objects and we photographed them in pairs. Now, the key thing about this stimulus set is that every object pair appeared in two relations, containment and support. And for each observer, we selected one of these images to be the target at random. The rest of the images were distractors. And these target and distractor images were embedded in a sequence, one after the other. So the task was to press one key for this target image and another key for all other images. A very easy task. But crucially, notice that sometimes the distractor images matched the target's relational category, containment, and sometimes they did not, like these ones. Now, remember the task involved responding to the exact image on the left. We didn't say anything about relations at all. The key question was whether, even so, people would confuse distractor images for their target when it matched the relational category, even when the distractor contained very different objects. Now you can try this yourself again. So let's do a demo. So here's your image. This is your target image. I want you to type F in the Zoom chat when you see this image and type J for any other image. So I can't actually see the chat, so I have no idea what you're typing, but I'll just assume that you guys are all doing this. Okay, so this is your target image. Get ready. Here you go. Now, there are a few things you probably experienced. So one is that it was really easy, and that was the intention. Now, you had to type, so maybe that made it a little more challenging, but people in our test just had to press the button. Second, you probably made very few errors, if any. But when you do make errors, they're pretty telling. And since we have over 200 participants, we can collect a lot of these rare errors. So that allows us to ask, will there be more confusions or false alarms when distractors match the target's relational category, even when that distractor contained very different objects? So here, I'm going to show you the results. On the y-axis is the proportion of false alarms for relational matches versus non-matches. So matches are where the distractor matches the target's relational category. Non-matches are where it does not. And as you can see, yes, we see more false alarms for matches. And a reminder, this task was super easy. So there should really be very few errors, and you can see that. But these rare events are more common for relational matches than non-matches. And we think that's because people are spontaneously extracting the relation from the images they're observing, in a way abstracted from the particular objects in that relation. However, of course, there's some alternative possibilities. So one is that maybe people discovered it was useful to make the distinction between in and on, to encode the relations in these images. So if you notice the following, if your target was knife in cup, one of the distractor images contained the very same objects as the target image. So if the target was knife in cup, sometimes people saw knife on cup. So our design sort of might encourage a strategy of encoding the relations, because encoding the objects alone is not sufficient to distinguish the target from every single distractor image. So a stronger test of our hypothesis would make the relation totally irrelevant. And so we did just that by running the same exact experiment, but we would always exclude the distractor image with the same objects as the target. So if the target was knife in cup, people never saw a knife on cup distractor. So here, extracting the category of objects alone is sufficient to perform the task. And when we did this, we saw a similar effect as before, more confusions for relational matches. So these results suggest that the effect is not just due to a useful strategy that our task encouraged. We think the abstraction of relations from their objects happens spontaneously, even when encoding object categories or other visual features is sufficient to do the task. So in a final set of experiments, we aim to rule out some lower level visual confounds. So for example, you can see that many of the containment images can contain more diagonal edges than the support images. So we addressed this issue by creating distorted versions of these images, such that low-level features were preserved, but the category of relation was not. So in the first control, we used box scrambling. We cut the image in chunks and rearranged the boxes. And this preserves some local features, so if there's a small diagonal contour in the original image, it's still here somewhere. And the next control is what we call diffeomorphic warping. And that's where we expand and contract the image as if it's on a rubber sheet. And what this does is it preserves most of the colors, textures, and sizes of the objects, but it destroys the impression of a relation. And together, these manipulations let us ask whether the previous effects were due to these lower level visual features that are correlated with the relations. So if so, we should see the same relational confusion effects here, more false alarms for the matches. But if it's not purely low level, then the effects should disappear. So we should see just as many confusions for relational matches as non-matches. And that's just what we saw. So the difference between matches and non-matches was statistically indistinguishable in both of these control cases. So these results suggest that the relational confusion effects we saw before were not due to lower level visual correlates of in and on relations. Instead, it suggests that the relations are spontaneously extracted from such images in a way that's abstracted from the particular objects involved in the relation. So let's return to the outline for today. So far we've seen that relational representations are formed over the course of visual processing, and they exhibit core characteristics of relations, so structure and abstraction. And this fact suggests that such representations may in some cases be compositional. So in the third and final part of my talk, I'll explore the nature of this compositionality. And this is work done with Chaz Firestone and Zekun Sun. Zekun is an awesome former student of Chaz who is now starting a postdoc this summer with Sam McDougall at Yale. So if the term compositionality isn't familiar, what it means is just a representation is compositional if it can be expressed as a combination of parts and the particular way those parts combine. So, for example, consider a sentence like "the cat is on the mat," which can be represented in sort of tree structure. You don't need to worry about that. But we can understand the meaning of the sentence by knowing the meaning of the individual words and understanding the way those words combine. And this principle can enable some powerful flexibility and generalization. So it supports your ability to understand unusual sentences like "the mat is on the cat." And you can understand this because the words are combined differently and you have a representation of the way those words combine, the rules. And the same goes for other unusual or even novel sentences like "the table is on the book" or "the shekel is on the banana." So this is not a real image, I just made it from DALL-E, but you get the point. So compositionality is traditionally considered a core property of language and higher level thought, but the work I've presented so far today suggests that at least some visual representations may also be compositional. So just as individual words compose together to form phrases and sentences, visual representations contain discrete entities like cat, mat, that combine in systematic ways. So compositionality is a kind of principle, but you can also think of it as a process, how things are built or combined. So if visual representations can be compositional, this raises an intriguing question. And that is, what is the nature of the compositional process itself? In particular, how are structured visual representations built up over time? And that's the main question for this part of the talk. So one possibility is that all the parts are sort of combined simultaneously. So the image itself has all that content all at once. So maybe the mind combines them all together at once. But here we explore an alternative. So that visual processing might build relational representations sequentially. But if this is the case, which object should come first? Well, here we take inspiration from an interesting idea in the cognitive linguistics tradition. So if we consider that our favorite sentence here, the cat is on the mat, the idea is that even though the cat is the subject of the sentence, it comes first in time, we actually interpret this sentence primarily with reference to the mat. And that's sometimes called a ground or reference object in this context. So reference objects are generally those that physically control other objects. So they're large, stable, etc. While figure objects are those that are often physically controlled. They're small and mobile, like our cat or a plant. So the cognitive linguistic tradition suggests that reference objects are considered primary in cognition. And on this perspective, the mental representation of a sentence like the cat is on the mat is such that there's a mat, and on the mat is a cat. If that's right, then what about the case of looking at an image of a cat on a mat? Might reference objects also be primary in visual processing? In other words, do we also process this image as a cat or as a mat, and on this mat is a cat? So we address this question in two complementary ways, through what I call a production task and a recognition task. So in the production task, we had people position objects to compose scenes that matched a sentence. And here's what it looked like. So here you're composing laptop on the desk, and you can choose which object to put in the frame first. And then you build the scene, and you press a button to move on. Here we have the plant is on the shelf. And your job is to just build the scene that matches. By the way, this is me performing the task. You can see how awesome I'm doing. So the question was, would people consistently prefer to place one object before another to build these scenes? And in particular, the reference object. Here, that would be the desk. So I'll show you the results. Here on the y-axis is the percentage of trials where people placed the reference object first. Above 50% means there was a consistent preference to place the reference object first. And that's exactly what we found. So every single participant on almost every trial placed the desk before the laptop, even on the very first trial. And this was really general. It held for different pairs of objects. It held for different kinds of relations, physical ones like on, and spatial ones like above. And it held no matter the word order, no matter which word came first. So these results suggest that reference objects are primary in relational scene production. But we next explored whether this pattern goes beyond such preferences and drives visual processing itself. And to do that, we use what's called a sentence picture verification task. So again, we presented people with a sentence like the laptop is on the desk, except here, the task was to verify whether this was a correct description of a scene that would appear a moment later. So if they saw this scene appear, it would be true because there's a laptop on a desk. Whereas if they saw this scene, the sentence would be false. And people had to do this really fast before the trial timed out a second and a half later. So crucially, sometimes the reference object, the laptop, appeared a half second before the figure object. Oh, sorry. Crucially, sometimes the reference object appeared, the desk appeared before the laptop, like this. Or vice versa. Sometimes the figure object, the laptop, appeared before the reference object, the desk, like this. So the key here is that manipulating this order lets us ask whether the mind has a preferred order for building relational representations from glancing at visual scenes. So if the mind really does this in a sequential way, then this task is almost like we're building the relation for them by showing these objects in the order that the mind prefers, whatever that order might be. And if that's true, then we should see it's easier to verify the description in one case than another. And we think that people will be faster to do so when the reference object appears right before the figure object, when the desk appears right before the laptop. So last time, you can try this task yourself. I'm going to give you a sentence, and your job is just to type Y for yes, if it's correct, or N for no, if it's not a correct description. And you have to try to do this really fast. All right, ready? So the laptop is on the desk. Now I'll show you the scene. I have no idea what you're typing, but I'm assuming you all typed yes. All right, the plant is below the shelf. The answer is no. Or yes, I'm sorry. Yeah, yes. Scared you guys for a second. The lamp is on the nightstand. So that was no. And here's one more. The table is supporting the vase. Okay, and that's yes. So maybe you already have a sense of whether the task is easier in one case than another. What about our participants? Will it be easier for them to do this when the reference object, like the desk, appears before figure objects like the laptop? So here are the results. On the y-axis is the reaction time for accurate trials. So on some trials, both objects appeared at the exact same time. And when that happened, people responded within around 750 milliseconds, pretty fast. But when the figure object appeared before the reference object, people were faster. The crucial question is, what about when the reference object appeared first? Now, as you can see, people were faster still. And the majority of people showed this effect. In other words, it was easier to verify the scene description when the reference object appeared before the figure object. And that's a reference-first advantage in recognition. And this effect held over different sets of objects, different relations, and word orders. So it didn't matter whether the description was the laptop is on the desk, where the figure comes first, or the desk is supporting the laptop, where the reference object's mentioned first. We saw the effect in all these cases. So these results suggest that the reference-first advantage doesn't just hold for preferences in how to build a scene, but also in basic recognition processes. This should say recognition. So next, we wanted to probe the time course of this process in detail. And luckily, psychophysics provides us with a tool for the job. So such work often manipulates the precise timing of stimuli to infer the time course of visual processes. And this is a well-established method across different kinds of visual tasks. And we're going to take advantage of this approach to study the time course of this compositional process. We ran the same study as before, but we introduced different delays between the first and second object. They could differ by 100 milliseconds all the way up to 1500 milliseconds. So here's an example of 100 milliseconds delay between two objects. You can try this if you want. So that was quick. They pretty much appeared at the same time, right? Here's one example of 1.5 second delay between the two objects. Here, the answer is yes, right? So let's see the results. Again, the y-axis is reaction time, and the x-axis is the delay between the two objects. The blue line will be for figure first trials, and the orange line is when the reference object appeared first. So at 100 milliseconds, they're almost exactly the same, but you can see the effect gradually increase up to 500 milliseconds. That's the duration we used in the previous study. But then you'll see it decays after that. So I think these results are pretty exciting because they show the sensitivity of this process to precise timing of the objects. And I think this pattern also implies that the observed effects are not, or at least unlikely to be the result of deliberate reasoning over which object should come first. What I mean is, yeah. Sorry.
Can I just ask if the sentence was the sentence present throughout the trial, or were you only exposed to it? Okay. Mm-hmm.
The sentence was present throughout the trial, just in case people didn't quite remember what the sentence was. But people responded pretty fast, suggesting that after a few trials, they pretty much memorized the sentence, right?
Okay, thank you.
Yeah, no problem. So I think these patterns imply that the observed effects are probably unlikely due to be from deliberate reasoning about the order they should come first. So what I mean is, if that were the case, one might expect the effect to increase and increase over time, because with longer durations, people just have more time to think carefully about the order of objects and prepare a certain kind of response. Instead, our effects peaked quickly and then they faded. Now, although this doesn't demonstrate that visual processing is the sole source of this observed effect, it is consistent with many well-known visual effects, such as attentional blink or backward masking, which are very sensitive to precise timing characteristics. So in a final study, we want to rule out alternative explanations for the reference first effect. So you might notice that there are some size and shape differences between these kinds of objects. So you can see reference objects are generally larger and they're more rectilinear than the figure objects, which are smaller and more curvilinear. And beyond that, we also have some real-world experience with the roles that these objects tend to play. So tables and desks tend to physically support things like laptops and lamps, not the other way around. So the question is, are results merely driven by these size or shape differences, or by prior experience with the roles that certain objects play? So in a final study, we directly test those possibilities. We ran the same paradigm as before, but with a crucial change. Instead of using objects that differ in size and shape, like a laptop and a desk, we used identical objects differing only in color. So a red book and a blue book. So in these cases, physical control, which object is supporting the other object, that's what determines the reference and figure roles, rather than any property that's intrinsic to any object. So for example, here, the red book is supporting the blue book. So the red book is the reference object here, and the blue book is the figure object. And once again, what we predict is a reference first advantage. Since the red book is the reference object in this case, it's supporting the blue book. We predict that people will be faster when they see the red book first, right before the blue book. So once again, here's a couple examples. The blue book is supporting the red book. Well, here the answer is no. The blue book is on the red book. The answer is yes. The question is it easier when the red object, the reference object here, comes before the blue book? So here are the results. So again, y-axis is the reaction time. And we again found a reference object advantage. So people were faster to verify the sentence when the reference object appeared first rather than when the figure object appeared first. Even when the roles of the objects was defined based on the physical relationship between the objects, not by any properties that were intrinsic to the objects themselves. So even though there were no size or shape differences between these objects, it was just physical control that dictated which one was the reference object. We still found that people were faster to identify the sentence when the reference object came first. So bringing it back to the question we asked, what is the nature of the compositional process, and in particular its time course? We found the mind composes relational representations sequentially from viewing visual images in a way that respects the role that each object plays in the relation. So here, for these kinds of relations, reference first, figure second. And more generally, I think our findings reveal something about the nature of the compositional process for visual relations. So stepping back, I've shown you just a few examples of a broader research program that takes relations themselves seriously as objects of study in vision science. But these case studies are part of a larger research direction from many research groups. And I've reviewed this growing literature in a paper published in Trends in Cognitive Sciences with Chas Firestone. We've recently developed these ideas a bit more in a commentary that was just accepted in Behavioral and Brain Sciences. And in our commentary, we expand on the ideas of the target article above by J. Quilty Dunn and colleagues. And we put together evidence for the existence of compositionality in visual perception. But sadly, there's only so much time in an hour, so I have to stop. But I'll end by saying I'm really excited to continue this kind of work at the University of Delaware, where I just started a position as assistant professor of linguistics and cognitive science. So keep your eyes peeled from the UD Perception and Language Lab. And if you have students who are interested in this kind of work, tell them to come be a pal. And with that, I'd like to thank my funding sources, my many collaborators, and of course, thanks to you for listening.
Alon, thank you very much. It was really interesting, and I'm inviting everybody to unmute yourself, and let's give Alon a big applaud. And I do have myself a few questions, but I'm willing to let others go ahead, and then of course I will have a go.
Yeah, no problem.
Well, I'll start.
Okay.
I see. So I've got a few questions. One of them is the issue of gravities that I was thinking about, because like in the actions that you showed, when people were facing one another or doing things to each other or not, there was there was gravity because they're, standing on some surface, but in general, the composition or the relation between them was kind of like not based on gravity. And in the experiment you did, like this was on, this was below, it was kind of like gravity was playing a role. And I was thinking whether if you look at relationships that are like right-leftish, would that change in a way? I mean, do you think you would find similar relationships, like he's pushed, he's being pushed? Do you think this is this would generalize across?
Yeah. Yes, I think I understand your question. So in other words, like in the third part, I sort of used certain kinds of relations. So I used physical ones, like one thing supporting another. I also used spatial ones, like thing above or below. I didn't use left or right because people are actually pretty bad at left and right for many interesting reasons. But with regards to how this would generalize to other kinds of relations, I think that's a super interesting question. In other words, you might think, okay, so in like an eventive interaction, like with agents and patients, like which role is primary, agent or patient, right? What's interesting is there's a lot of work from like language that suggests, agents are primary in those cases. So they come first in the sentence, they appear in the subject position. So in one case, on one hand, they're primary in that sense, but on the other hand, patients, like people who are being acted upon or things that are acted upon, are also primary in some sense. So if you look at like a linguistic structure, like a syntactic structure, they're the thing that's embedded in the verb phrase, like the agent's like outside of it doing its own thing. So I think it's a super interesting question that I would like to address, asking about sort of like what is the primary role in a visual image of a relation, like an event, right? I think there's might not be a clean mapping from like figure and reference in spatial and physical relations to things like agent and patient. I don't know which would be first.
Yeah, this is really interesting. And I'm wondering what you said, that people are much worse in right-left relations. I'm wondering if that has to do with the visual statistics that we've encountered across our lifetime, where, you know, gravity is a very dominant force we see every day, and things that are pushed or being pushed rightward or leftward are, you know, in the horizontal, let's say, axis would not be as prevalent as things that are, you know, as gravity, for example. I mean, clearly.
Yeah.
Do you think this has to do with maybe the statistics of the, I don't know, of the visual scene that natural statistic that people encounter?
Yeah, so that's a great question. So for these, you know, object viewpoint invariance, like in a sense, it doesn't matter whether something's flipped left, right. It matters a lot whether something is flipped up or down because of gravity reasons, for example. So I think that is a very plausible explanation of those kinds of results, right? I'll just say also something that's interesting about these physical or force dynamic relations, like on or containment, like support or containment, that's different from some of these spatial ones, is that a reference frame. So what I mean is, if something's in something else, the reference frame from like the viewer to those objects, it doesn't matter so much. It's always just in because of the physical relationship between those things. Whereas for spatial ones, it matters a lot what your viewpoint is. Like if I flip upside down, you know, changes which one's above or below. But more importantly, if I am at a different angle from like these two objects, which one is on the left and which one's on the right is different. Even for occlusion, right, which is a spatial relation, occlusion will happen depending on my viewpoint of the objects. It's like a spatial relationship, whereas physical ones are really defined by like the forces between objects. And so I think there's more potential for like those to be special in some way in cognition and even in vision.
Thank you. Very interesting. And Hagit, you've got a question?
Yes.
Hello.
So first, hi, and thanks for a great talk. I enjoyed it. I'm referring, actually, the question sort of refers to what Sharon was asking in terms of gravity. It could actually be maybe explained in your third experiment with the books. If you just change the sentence from the red is on the blue to the blue is under the red, the reference would change, but the stimuli would be exactly the same. Would you see a flip in the response time then?
Really great question. So in those experiments, we flipped around word orders because of this worry, like, is it just whichever object comes first in the sentence, for example? So we had things like the blue book is on the red book, but we also had the red book is supporting the blue book. Something I didn't talk about for simplicity reasons is the really interesting case in that study. What happens when, so those objects are identical, right? What happens when you have the spatial relations above and below? Now, which one is actually the reference and figure? So in that case, there isn't, right? At least there isn't a reference and figure defined by the scene, by the world, right? Because they're identical, like this object and this object, they're spatially separate. Right. So in those cases, what actually drives the effects is the sentence structure, what you're saying. So I didn't want to go into this whole thing for like sort of time and complexity reasons, but you know, the cognitive linguistic tradition I was telling you about, if you have something like the cat is on the mat is in object position, you could think of it, right? And in a sense, the sentence structure is sort of also telling you which one is the reference object. It's the one that's like in the object position, right? So if you think, here's an example, if you think of like the bicycle is next to the garage, that makes sense, right? You could think of an image where that's the case, like bicycle, big garage, bicycle's here. What about the garage is next to the bicycle? That's a really strange sentence, but you can still interpret it. you just might think of like a garage on wheels, like a little one, like rolling around a giant bicycle statue.
But you're giving it a size interpretation, right?
Yeah, the sentence is in a sense dictating,
Right.
like it's like making you attribute certain properties to those objects that you're describing in the sentence.
Right, but the point is that you sort of infer the reference from the sentence. But if
Yes, in the cases where there's ambiguity in the visual scene or the physical situation, the sentence is sort of what dictates which one is reference object and which one is figure object.
So
But
you're saying that even if the sentence is the red book is under the blue book, the red is still the reference because it's supporting something else? I mean,
yeah, under is a strange one that I have to think about more. But if you say something like the red book is supporting the blue book, in those physical situations, gravity and physical forces sort of disambiguates which one's the reference and figure object. That dominates the physical relations. In the physical relations, those physical relationships dominate. So even in the case where the word order is flipped, you still find these effects of like, it's just about which one is doing the supporting. But when you have these ambiguous cases, like the objects are the same in many ways, and there's a spatial distance between them, then it's the sentence that drives your interpretation of which one's the figure and reference.
And then you see the flip in the response
Yes.
time.
So for example, if I say the red book is above the blue book is the reference object. If I say the blue book is below the red book is the reference object.
And you'll respond quicker when that reference appears first on the same, right? The stimuli and the end is the same, but which one appears first is, right.
Yeah.
Good. Thank you.
So there's this complex but interesting interaction between like linguistic interpretations of sentences and like your visual interpretation of a visual scene. The visual sort of dominates when there's not much ambiguity between the properties of the objects and whether they should be reference objects or not. But when the visual scene is pretty ambiguous as to which one should be the reference object, the sentential information sort of takes over, and whichever one is like, if you want to think of it as grammatically the reference object, dominates.
Okay, and maybe if I can, just one more question. The image with the cat and the mat, the cat was enormous and the mat was really small. So, and the mat was relatively small. So it was kind of strange for me to think of the mat as the reference because the first thing visually would pop out the cat just because of the size.
It might not be the best example, I'll admit that, right? By the way, that's my cat. That's my cat. I took him when he was 3 months old. I tried lowering a mat on strings, which was not successful. So I just waited till he fell asleep and then just gently placed this mat on top of him.
The
he's a big cat
challenges
now.
of being a scientist, right?
Yeah, at 3 months old, he was already like in science, but now he wouldn't let me do that. You're right. Mat is not the best example of it's not the most canonical reference object, I think. So yeah, you're right. I agree.
Okay, thank you.
But it rhymes with a cat, so that's good.
Yeah, and it's a classic sentence people use when they're talking about like in language research.
Lovely. Are you happy to take more questions?
Yeah, I'll stay here for, I mean, this is my
don't
morning.
commit
So I have all
yourself.
day.
Let's see how it goes.
Yeah.
Okay, so Ellie, do you want to unmute yourself? Do you have a question? What you have to let me I'm asking you to unmute because you are on.
More of a comment.
Okay, hi.
You may see that I'm in a car.
Yes.
And in a few hours, I'll be in Delaware.
What?
Just a coincidence.
No.
I'm driving through. So.
Okay, stop by.
Yes, yeah, maybe some other time.
Okay.
But the other comment I wanted to make is that the right, left, up, down is interesting if you think about mirror. In a mirror, right and left are switched, up and down is not.
Yeah.
It's a bothersome thing to think about because the mirror doesn't know about right, left, and yet it has this relationship.
Yeah.
So it may be of value for you. And the same relationship of switching is, of course, occurs when you're facing another person. So the right, left. So it's just a thing that has been on my mind many times, and I thought it may be relevant to this issue of why left and right are different than up and down in
Yeah, yeah,
your
yeah.
area.
Thank you.
Otherwise, it was very interesting.
Okay, thanks. Yeah. I'll see you soon.
Thank you, Ellie. I was thinking in Delaware, that's another relation, and
Of course.
I also have another question. I mean, given that, so first of all, you said that your tasks were extremely easy, and I was wondering if you thought about a way to make them more difficult so that the effects would be more robust. So I don't know if to make the visual scene more difficult, or just to just ideas that I had in mind is just to display the sentence and then eliminate it. So people will have more, maybe it will be more demanding for them to actually remember the sentence, and then they will just make more errors. I'm not sure. Just a thought. And even I was thinking of, you know, maybe binocular rivalry of some sort, where you like the scene is it takes more time for it to penetrate, and maybe you would see that things that are of one of the conditions would be popping into awareness sooner than others. Just thoughts. And then based on the idea that most of our relations are built on our visual experience, like if we would see something that is completely something we haven't been exposed to in reality, or cannot infer from what we've experienced about it, that would be really odd. So I was thinking about maybe taking snapshots of videos taken from spaceships where gravity and all these you know, forces are very, very different from what we experience. And you've got astronauts who are doing, you know, water, you know, everything is very weird, and all the relationships are completely not as we typically, you know, human beings are. And I'm wondering if then I don't have my mind completely straight. I was thinking this could test some of your ideas, and maybe even examine how experience dependent these representations are.
I love it. Sorry, go on.
And I did have another thought, which now
Great.
evaporated into space. But I will write to you as soon as it comes back.
I can address some of your questions. First of all, you know, I think it's an open and interesting question as to how these things emerge from experience. You know, maybe there is even some sort of inbuilt machinery. I don't have any evidence for that in my work, but there's a lot of work with infants suggesting they understand and reason about relations, like at a super early age, even before they might reason about object categories. You know, for the experience thing, like, you know, what was I going to say? Darn it. You know, first of all, we can use Blender. We don't have to go to space. Luckily, there's software that lets us manipulate the physics of these scenes, which is nice. You know, I think it's very possible that, like, you know, people will be really good at adapting to those things through experience. Like, they'll realize that gravitational support in space is not a thing, right? Other kinds of support are like attachment, right? Things attached to other things. Those actually are harder for kids to learn, and my own, you know, thoughts is that those things might even be harder to extract perceptually, because like the gravitational support is a super robust and early arriving kind of representation we have. But I think in a way the third part of my talk sort of gets at this question a little bit. I think the fact that we might, just like with sentences, like the fact that we have a grammar and we understand sentences through composition, like through understanding the way parts combine, lets us rapidly, like, you know, understand sentences that we've never heard before, because we have representation of the individual elements, and we have rules for how those things combine, such that we can interpret new sentences that we've never heard before. And that's why you don't have to be exposed to like lots of new sentences many times in order to understand them, because you have individual representations of the parts in a separate way from the way those combine. And I think if vision in some sense or some cases can do composition in sort of analogous ways, like you represent the individual objects and you might have rules or ways that those parts combine, it lets you rapidly assign meanings to spatial or physical situations you've never encountered, even with new objects, right, etc. I've never seen a blork or a glimbit because they're from Mars, but I still can tell that a glimbit is on top of a blork or whatever, right? If you had
Or
to,
not, yeah.
yeah, if you had to have visual statistical experience with every possible combination of everything with every other thing, you'd never be able to do that. So I think this might help address some issues with like generalization, especially in a lot of the new AI. They're getting really, really, really good at like being able to do this with novel situations, but in my own opinion, they're sort of approximating this compositionality rather than maybe in humans, it's sort of just the nature of the system. And then finally, you mentioned something about like attentional, no, what would you, continuous flash suppression, was that what you said?
Yeah, continuous flash
Or
suppression,
binocular
exactly.
rivalry. Yeah, so I didn't do this, but there's some work asking about like causal events like collisions in terms of whether they reach awareness faster or break through faster than sort of matched non-causal events, and they find some evidence that that's the case. So, like I said, this is like a lot of research done by lots of different labs focusing and converging on these topics. There's work that I think shows even more than my work does that at least some of these relations are extracted like really through the visual system. There's like retinotopic adaptation for some of these things. Yeah, and so, I can't answer all those questions, but I think
No,
the
of
evidence,
course.
the vision playing a larger part than we might expect in extracting these relations, representing them in sort of a compositional way. So yeah, as for like the size of the effect, yeah, that's always a tough thing, right? The more I make the task involve or about relations, the more, higher level cognition can be like the cause, or we can attribute it to cause. Like if I just say, describe this image or rate it for me, I don't know what part of the mind is doing the work. It's tough. I get super large effects, but I don't know like whether it's vision, language, cognition, or whatever. However, the more I make the relational information irrelevant to the task, the smaller and smaller the effects are going to be. So, in the third part, the effects were pretty strong. Like there were tens of milliseconds between the different conditions. In the first part and the second part, the effect sizes were huge, like Cohen's D's of like 1.3 and stuff. But the absolute magnitudes were, I will admit, quite small.
I see. And
Yeah.
okay, two more. Okay, I'm gonna finish at that. I just want to ask, because you are the language expert, or I'm not at all, whether language or language structure has any influence, like across cultures or across languages, whether you would find differences. And another question is, if you think like, physics wise, you have attractions between different objects. And if you find, for example, in your data, if you have looked into, the people doing actions one on or towards the other in a way, when you flip them in Photoshop, do you find that people are faster when the items are somewhat connected or attached than when they are not?
Yeah, so yes, and so there's work from like Liuba Papeo, who does a lot of work on how you extract like relations between two individuals or like two bodies facing each other, let's say. There's like a lot of sort of Gestalt grouping effects. There's advantages for like, inversion effects. There's a lot of advantages in visual search for like facing away people versus facing apart people, facing towards people versus facing apart people. So the idea is basically the visual system might have like a template or a way of extracting facing bodies that's special from ones where they're facing away. And even in my experiments, I find the condition where people are facing away, on average, people are just slower to respond to my task by 10 milliseconds, which is
really
a lot
cool.
for the size effects. And if you remember, they're not doing like an event task. They're just pressing the button for the side of the person. So you might think it's more surprising that it's harder to do that task when people are facing away. There's some way in which like a tension is spreading between the individuals when they're facing towards each other or something like that, so that people are just faster at these orthogonal tasks.
Interesting. So thank you very much for this really interesting talk. And yeah, and thanks for joining us. And we will be back here in 2 weeks. Next week we don't have a talk. In 2 weeks we'll be continuing. I will be posting the details. So Alon, really, it was a pleasure having you here, and thanks for joining us again.
Yeah, thanks, Sharon, and thanks everyone for sticking around. And I might look at the chat transcript later just to see how well you guys did at my demos. We'll see.
Okay, wonderful. Thank you.
Yeah.
And
Thanks
bye.
a lot.